This video is on breadth-first search. It's the third video of a playlist on basic graph algorithms, following an introduction to graphs and how they're represented. If you just watched those, wake up. Breadth-first search is conceptually simple, easy to implement, and worth understanding fully because several algorithms you'll see later are minor modifications of it. We'll see an overview, simple and more detailed implementations, breadth-first search trees, analysis, and after that, I'll hand-wave a correctness argument. Breadth-first search can run on directed or undirected graphs, and we ignore any weights. I'll show it on a directed example, and especially for analysis, we'll assume an underlying adjacency list representation. The basic idea of breadth-first search is that you have a starting vertex, and you explore vertices in order of how many links they are away from it. First, explore the starting vertex, then all of the vertices 1 away, then all the vertices 2 away, and so on until you hit all vertices reachable from the original one. Here, each reachable vertex from the start vertex has an edge from the level above it, but not from any higher reachable vertex. And in this case, we have a couple of vertices that aren't reachable, okay? That's the whole concept, and if you're looking for the shallowest of understandings, you're done. For that visualization, I started with vertices already in a position to easily see how many links they are from the start node, but the computer graph model doesn't really need any location for vertices, they're abstract. We can put them wherever we like to visualize what's going on. Just for our simple implementation of BFS, let's put them in a more arbitrary position, and we'll see that it's hard to see what's going on. Like with most graph algorithms, assume that each vertex has some room in it that the algorithm can use to store information. At the very least, the algorithm needs to mark each vertex as discovered or not. When you start, initialize all vertices as undiscovered. Next, mark the start vertex as discovered and stick it into a first in, first out queue. After that, the algorithm is just a simple loop. While the queue isn't empty, dequeue a vertex. For each of its outgoing edges, if they go to an undiscovered neighbor, discover and enqueue it. That's a simple breadth-first search implementation. The only thing it accomplishes is to mark the vertices which are reachable from the start vertex. Running this algorithm implies a specific breadth-first search tree. The root is the start node, and if one node discovers another, it's that node's parent in the tree. For the same graph, you get a different breadth-first search tree based on whatever node you pick as the start node. Our detailed implementation will calculate this tree and also store the number of links needed to reach each vertex. Again, assume there's space in each vertex to store extra information. Store the number of links initialized to infinity, and also for each node, store the second to last vertex used on a path from the starting vertex. Using Cormen's notation, I'll store it in a variable called pi, which stands for parent or predecessor. Initialize that to nil, and we step through the algorithm again, a bit slower. If we start with the nodes in these positions, it'll make it easier to see it as we run through each vertex and edge. So the start vertex is discovered in 0 links, and each time you discover a node, it gets discovered in one more link than the node that discovered it. Notice as we go that the queue only contains 1 or 2 different distances in it at a time. We won't add any distance 3 vertices until we remove a distance 2 vertex from the queue, which only happens after all distance 1 vertices are removed. As we go, for each node, save which vertex discovered it in its pi value. That can be used to reconstruct shortest paths from the root to any vertex with a short recursive algorithm. It finds a path to the parent and then adds the last vertex at the end. The union of those paths will make the breadth-first search tree. The start node's children are the nodes it discovers, and so on. The more connected a graph is, the more bushy its breadth-first search trees tend to look because vertices in the queue early will discover more children. For this run, we see that A is a child of B and not of F. That probably happened because in the start vertex's adjacency list, the edge to B came up before the edge to F. B enters and exits the queue before F, beating it in the race to discover A. One minor change in my algorithm compared to the one given in the Cormen book, instead of marking vertices as discovered or undiscovered, they use 3 colors. White for undiscovered, gray if it's discovered but not yet finished when it's in the queue, and black for after it's finished. That's it, the full implementation of breadth-first search. For a quick analysis, the initialization takes time linear in the number of vertices in the graph. After that, each reachable vertex can only be discovered and then enqueued once. A vertex's outgoing edges only get explored when it's dequeued, which can also only happen once, and takes time proportional to the number of outgoing edges for that vertex if we're using the adjacency list representation. For an undirected graph, reachable edges can be explored once from each side, but still that gives us a total linear time in the number of reachable vertices and edges. So we can write exact theta notation using reachable edges, or use big O upper bound notation in the size of the graph as a whole. For many of you, that's probably all the detail you want, but you know you really should know something about its correctness. If you really want to understand a more formal proof that the algorithm works, the best way is to figure out the details for yourself, but here's a quick outline to get you started. The first thing you need is a more formal statement of what the algorithm is supposed to do. Informally, it reaches all the vertices reachable from the original vertex, and for each of those vertices, it finds a distance and the previous vertex on a path from the start vertex. Non-reachable vertices get default values. Next, you need to prove something about what the algorithm does. Here are a couple of statements that can help you in your proof, where each statement can be proved by induction. We're also assuming that the first in, first out queue gives you items in a first in, first out order. You can work these statements more fully if you want a real understanding, but I figure if I hand wave enough, you'll imagine that I could prove it if I really wanted to. Up next in the playlist is depth first search. Please subscribe.